Well, standard free energy, that only applies in a very narrow set of conditions, right? Standard conditions. If we look at water being transformed from a liquid into a gas, delta G for that is a positive number. And that's not per meter. The O and the L got lost in this hallway. So delta G is greater than 0. The process is non-spontaneous. But what happens if you spill water on the floor? Does it stay there forever? No, it evaporates spontaneously, right? Why? How? It's not at standard conditions. So if you're under standard conditions, the vapor pressure of the water is 1 atmosphere. The vapor pressure of water in this room is not anywhere close to 1 atmosphere. It's really, really small. Ordinary conditions, the vapor pressure of water is much, much smaller than 1 atmosphere. If we want to predict spontaneity under non-standard conditions, then we need to calculate delta G under those non-standard conditions. So here we're calculating delta G without the degree symbol, right? This isn't standard. This is delta G, the free energy change of a reaction under non-standard conditions. And we have this equation. Delta G is equal to the standard free energy change plus RT times the natural log of Q. And just a reminder, when you're doing pHs, it's base 10 logarithms. It's not natural log. Here it is natural log, and yeah, it does matter. So Q is that reaction quotient that's been coming up every now and then. That's the reaction quotient. T is temperature in Kelvin, and R is the ideal gas constant in units of joules per mole Kelvin. So that's the 8.314 value. We talked about Kp and Kc, equilibrium constants for pressure or concentration. And Q has 2 varieties as well, Qp and Qc. So if we've got a reaction with just gases, we're going to use Qp. If we've got solutions, we're going to use Qc. So here's another one of those graphs. So here's the equilibrium equation, right? H2O liquid going to H2O gas. How would you calculate the equilibrium constant for that? Well, it's the concentration of products over reactants, but liquids and solids don't change, so they don't come in there. So it's going to be the concentration of H2O, or the pressure of H2O, right? So the pressure of H2O at any given time, that's our Q. Remember, Q is calculated the same way as K, but it's just not necessarily at equilibrium. So if we have standard conditions, Q will be 1, because the partial pressure of the water has to be 1, because that's the standard definition, right? And then we'll end up with delta G is equal to delta G, the standard delta G, plus RT natural log of Q. Well, the natural log of, that's RT natural log of 1, and that whole thing is equal to 0. So at standard conditions, these two are the same. If Q is 0, that means there's no water vapor present. Delta G is going to be negative. And so the water will evaporate spontaneously. At some point, Q will be equal to K, and there we've got equilibrium. If Q is greater then K, then water will condense. The reverse reaction is going to be spontaneous. Here, delta G is going to be positive. Any questions? Does that make sense? I always wonder about these. So at 25 degrees Celsius, liquid water is in equilibrium with water vapor at a pressure of 0.0313 atmospheres. So that's Q. So here we've got our reaction here, and this is the standard free energy change, positive 8.51. And here's our equation. Delta G under these different conditions is the standard delta G plus RT natural log of Q. So we'll put in our standard delta G plus RT, so that's 8.314 joules thermal Kelvin, times the temperature, 25, so that's 273.15 Kelvin. And the natural log of Q being 0.0313 atmospheres. Yes, thank you. Yep, just seeing if you're on your toes. That's what we added to the 25, and we got 298.15. Thanks. We need to be careful with our units here, right? This is joules. Those guys are kilojoules. So let's fix that. Get rid of the K and write what it means instead. So 8.59 times 10 to the third plus 8.314 times 298.15 times the natural log of 0.0313. I think I did something wrong. I'm offended my calculator in some way. It was telling me that that it was positive, which just doesn't work out. So I'm going to do this backwards. No, it just is. 3.03 joules. So, took my brain a minute to process this. It says at equilibrium, delta G for the reaction is 0. Well, we just calculated it and it wasn't 0. How big is this relative to 8,590 joules? 3 is pretty small. So no, we did not come up with exactly 0, but it was really close. So the reaction is not spontaneous in either direction. somehow my brain was expecting a negative delta G and the water would evaporate. But I missed something. I said it out loud, but my brain didn't process. The liquid water is in equilibrium with its water vapor. So is that reaction going to go in one direction or the other? No, it's at the bottom of the hill, right? It's just going to stay there. Now, there's water evaporating, but there's also water condensing at the same time, and the amounts of reactants and products aren't changing. Any questions about that? Yes.
So since it was at equilibrium, we shouldn't have even calculated it?
Since it was at equilibrium, we didn't even really need to calculate it, yeah. Let's look at other non-standard conditions, okay? On a dry day, the partial pressure of H2O is 5 times 10 to the minus 3 atmospheres. Calculate delta G. What was it, 859 kilojoules? Whoops. 8.59 kilojoules. I need that number. .59 kilojoules is that many joules. So we're doing this delta G at these non-standard conditions is delta G standard plus RT natural log of Q. So again, we've got the R, actually that's joules per mole, times the temperature. Doesn't tell us what the temperature it is. It's probably 298.15. And we need the natural log of Q. Well, what is Q? We talked about it, but maybe we forgot. This is our chemical equation that we're looking at, water going from the liquid to the gas state. And to calculate the equilibrium constant, it's going to be the concentration of H2O. So Kc would just be the concentration of H2O gas, or Kp would be the partial pressure of H2O. So here we're going to use the partial pressure, so natural log of 3.00 times 10 to the minus 3 atmospheres. Yes, it does. This is how we calculate K. That would be at equilibrium. Here, this is not at equilibrium, and so Q is equal to the partial pressure of water. I know it's a little confusing, isn't it? So now we're getting negative 4.544 joules per mole, or negative 4.54 kilojoules per mole. is it spontaneous now? Yes, it is. And thinking about this, the water will continue to evaporate until this pressure is equal to the equilibrium constant. This is very simple because there's only the one product and we don't have to worry about the reactant. But it's just going to keep going until we get to that pressure, which we learned from the previous one is 0.0313 atmospheres. Any questions? So consider the reaction at 298 K. We got H2S plus S2O making rhombic sulfur and water. We got our delta G. It says calculate delta G under these conditions. Is the reaction more or less spontaneous than under standard conditions? Well, all of these are gases, so if we were to calculate K, it would be Kp, and that's going to be the pressure of, oh no, wait a minute, that's the solid, right? So that doesn't come into it. Here's our gas, so it's the pressure of H2O cubed. Well, that was not a good place to start writing that. Let's just do it down here. It's the partial pressure of H2O to the second power. I don't know what was going on up there. That was a bad place. And the partial pressure of the H2S raised to what power? The second power times the partial pressure of SO2. And that's just to the first power. So at equilibrium, these pressures will equal whatever K is. We're not at equilibrium. We calculate Q the same way. It's the same equation. So the H2O squared divided by the H2S squared times the SO2. So that'll be more spontaneous. That's not the number I got. What did I do wrong? Of course, I might have typed the answer wrong. You guys get 129? Okay, we'll go with that.